So this presentation talks about our SimCenter solutions for experimentally testing the thermal characterization, reliability, and quality of electronics and semiconductors. So if we look at electronics, we know that things like temperature, vibration, and humidity can be very harmful to the reliability of the electronics, and especially the temperature aspect. Being a high temperature or fluctuating temperature can be very vulnerable to damaging the electronics. And that's why it's very important to understand these failure mechanisms, in this case specifically towards temperature. So if you look at a typical electronics build-up or package, as depicted here, we see that there can be a lot of places in the build-up in the structure of these electronics where damage can occur because of thermomechanical stress. It can be in the wires, can be in the connections between the chip, the base plate, etc. It can be in the die attach, the solder joints, etc., etc. So again, it's very important in case we want to study the reliability of the electronics and guarantee the quality of these electronics, that we also understand where temperature changes mostly affect our structure and risk to damage it. And so if you talk about temperature in electronics, there are several methods to measure that experimentally. You could use thermocouples, infrared cameras. Of course, if you point those to your electronics package, they will only give you information on the surface temperature from the outside of the electronics package. They will not tell you how the temperature distribution or the heat dissipation happens inside your electronics package. And that's a bit of a problem because that's important to understand. All the heat is generated at the junction, at the chipset, and is then, or should then be as fast as possible, as efficient as possible, be evacuated towards the environment to cool down the electronics and to limit the effect, the negative effect of temperature and high temperatures on your electronics. But so thermocouples, infrared cameras, they don't give you all of this information. They certainly don't tell you what the internal structure is of your electronics package. So you could use other techniques, like cutting open your electronics package to understand what the internal structure is and where maybe there is already damage occurring. But that's of course a destructive technique. There are also other techniques like acoustic resonance, etc., X-ray, but again, they don't give really the information of the thermal flow through your structure, or at least not without damaging it. So we need here a different technique, a different experimental technique, and that's in fact what we offer with our SimCenter MICRET solutions. So you see here depicted already one of our measurement units, the SimCenter MICRET Thristor, to which we connect our electronics or our electronic packages. And the difference with the previous methods is that this is a purely electrical test method, according to some JEDEC standards that you see here. But it's a pure electrical test method, which means that we use the existing connectors and wires on your package. We don't have to damage your electronics. We just easily connect 4 wires to existing connectors, and we're ready to measure and to understand the internal thermal structure of these electronic packages. I'm not going here in detail to how it exactly works. There is a hidden slide behind that explains that. But in fact, if we take again the schematics of a typical electronics package, like here with the chip, the die attach, the base plate with some thermal paste to the heatsink and then to the environment. The result of this measurement is what we call a structure function, and that's what's depicted here in the middle. It's in fact a curve which depicts the thermal resistance in a horizontal axis and in the vertical axis, the thermal capacitance. And you will see a curve appearing as a result of the measurement. And this curve, in fact, represents how the heat flow, or how the heat can be dissipated from here at the left side, the junction, towards complete right side in black, towards the environment. And you see that this curve, this structure function, which depicts, in fact, as we said, the thermal resistance versus capacitance, we see that there are some levels in there, some different levels, and those levels correspond exactly to some physical elements within my electronics package. So the purple one represents the behavior of the chip, then the green one is the die attach layer, then we continue to the base, the grease, the thermal paste, and finally in black the heatsink and basically the environment. So this structure function literally is a fingerprint about the thermal behavior, the thermal structure of the internals of my electronics package. And remember, we obtained this curve by just using existing connectors. It's a non-destructive method, a non-invasive method. So this was a bit a schematic representation of the structure function, but the graph you see here at the right side, that's a really measurement that we did on electronics component, and where you again recognize the different areas that correspond again to the different elements, physical elements within my electronics package. So that's very nice, but yeah, what could you use that curve for? It's very nice that we have this fingerprint identifying my electronics package, but in practice, how do people use this curve, and why is it so important to have it that accurate? There are a number of applications that I want to talk about here. So first kind of information that you could extract from this curve is, of course, your thermal metrics, your junction to case, to bore, to ambient, or some other thermal metrics that you might have to measure to put in the technical documentation of your electronics or electronics package, and that you can easily derive or read out from this curve. So measuring the curve experimentally, reading out those values will tell you what the real thermal metrics are on that particular package, and you can put them as such in your technical documentation. That's one possible application. Another possible application, or another very important information that this curve gives you, is it helps you identifying defects. Remember, I talked about techniques like X-ray to try to detect and look inside the electronics and try to detect where there is possible damage. That might work, but those techniques are not that accurate. The nice thing about the structure function here is that it will also show if damage occurs. Because let's say you have measured a good component where you know there is not damage, and let's say then you want to compare that with a component on which you know there is damage, maybe after using it for a while, or because you suspect there are production faults. If you measure both components, if you measure the structure function on both components, if they both would be perfectly okay, the two curves would perfectly match, of course. But if one has some defects, you will see that in some areas, some zones of the structure function, the thermal resistance would increase. For example, if in the die attach there are some air bubbles appearing or some impurities appearing, this means this will give a higher thermal resistance. It also means that this part of the structure function, which corresponds to this physical element, if the thermal resistance grows, it means it will shift the whole curve from that point on to the right side. You can immediately see by comparing those two structure functions, depending on which area in the structure function suddenly gets a higher thermal resistance, you can immediately relate that back to the physical component or element in your package which is responsible for this error. So again, non-destructive, without opening the package, without having to destroy it, with a pure electrical testing method, you can detect where damage is occurring. A third possible application is the combination with simulation. You might have a simulation model of the thermal behavior of your electronics package. In building that simulation model, you might have taken a number of decisions on material properties, geometrical thicknesses of elements, which are maybe not exactly correct. So if you want to improve your thermal simulation model, you can actually do that based again on this structure function. So what we do, if you can measure the real component, the real electronics package using the Tristor technology, then again you get this structure function which characterizes your package. You can import this structure function in, for example, our FlowEFD or FlowTherm solutions. And you can let the simulation model that you created there also let that one calculate the same structure function, but from the simulation model out. And then if you compare both curves, the experimental one, which is the reality, of course, and the one which is created by your simulation model, probably you will see some deviations. And what we allow then in the simulation packages is to define some parameters to play with within certain boundaries, and to do like a design exploration by changing all these parameters until you find a good match between the reality, which is the measured structure function, and the one that is predicted by your simulation model. And once you have that set of parameters tuned so that both curves match, then you know that you have a very accurate simulation model that you can further use in your further iterations in simulation. So calibrating your thermal simulation model, correlating the experimental results with the simulation results. Another possible application is what we call power cycling. And what you will do with power cycling, mostly used for like power electronics, is you will switch on and off these electronic component for a number of cycles, 10,000, 100,000, millions of cycles. So you're not only applying an on-off power to these electronics, that's what you could do, and then you wait until the component fails or until you reach the prescribed number of cycles that it should survive. You can take it off the machine and you can check if it still works properly. That's one way to do it. But of course, during or until the final breakdown of this component, damage is building up. And it's sometimes important to understand how this damage is building up. And what is the cause and the effect, because damage might occur first at one location and have as effect that at another location in your structure, secondary damage occurs. But you will not know that if you test until final breakdown of the component. So what we do instead, we combine the active power cycling with what we call monitoring. So now and then, after every 10,000 cycles, for example, we will measure the structure function. And then we continue the power cycling, and after the next 10,000 cycles, we take another snapshot, another fingerprint, another structure function on the same electronic component. And we keep comparing those. And what you will see happening is that first, the green curves at the initial number of cycles, they will still align very nicely because there is no damage building up yet. But the further you apply this power cycling, you will move to the yellow, the orange, and the red curve. Because if at one point in your structure damage is building up, maybe the component is still working, you will not notice, unless you compare these structure functions. And so this whole mechanism of combining active power cycling with monitoring is quite unique. These tests can run for weeks, so it is important also to have remote access to these test setups and to be able to monitor how the degradation is progressively happening. And it will also explain you what the weak points are in your buildup, in your electronics package. And it will give you the answers on where you should improve your design in order to avoid that it breaks down after this X number of cycles. So reliability, making sure that your component survives the prescribed life cycle of the product, very important. And that's something we can do with this technique. And the last one I want to talk about is you can even use this in your production environment where you're going to finally produce the electronic components. You have your production line. And if you want to know what the quality is of the produced items, or if you want to monitor, for example, some production parameters, like even materials used, etc., you can do this with our quality tester. That's an end-of-line quality testing, where we do, in fact, the same fingerprint testing, the same structure function. We measure it on possibly every sample that rolls off your production line. It means there's sometimes a robot integrated that picks up every electronic component that you produce. It puts it on a test station. It runs the Trister measurements, generating the structure function, and it compares it to some theoretically ideal curve. There might be deviations. If the deviations are small, you can decide that this particular component is still okay. If the deviations gets bigger and bigger, you might use it for some binning to put your product in different quality scales. So you can have your highest top quality production, you can have maybe a little bit less high quality product, and then you can have the product where it deviates too much, where you say, well, this I don't want to keep, I just throw them away. So very automated procedure of testing every sample that runs off your production line, and to test it and to bin it into a certain quality category that you predefine. So that's a bit the message here. We can help you with this SimCenter Micre technology in every stage of your development, being in the very early research, being it correlating it with your simulation models, being it when you do reliability testing and wanting to predict the lifetime of your product, up to the final end-of-line quality testing. So if we talk about industries, electronics, they are everywhere, of course, but if you want to group them a little bit together, where all these techniques I talked about are applicable is, of course, in the semiconductor industry, semiconductor packaging, people building IC components, packages, etc. Then these semiconductors, they go into different products, of course. Think about all the consumer electronics, like displays, everything with mobile communications, laptops, etc. Household type of products like HVAC. There's a lot of electronics in there. Then if you think about bigger scale, like energy industry, think about wind turbines, where there's a lot of energy conversion that needs to be done, where you have power electronics involved to convert the energy, AC, DC, and vice versa energy. Solar panels as well. The energy in your solar panel needs to be converted. And that again is done with power electronics. Automotive, think about EV, electric cars, hybrid cars. There also you have power electronics that convert the energy of the battery into your electrical engine. Not only automotive, of course, but also think about railway, about even aerospace type of eVTOL. So type of machines or products. And then the last one, which is very important, is of course power electronics, where there is a lot of new materials, new concepts being developed, because the trend there as well is that everything should get smaller and smaller, and the power that is inside these devices is going upwards, of course. So you have more power density, also thermal power density into these power electronics, experimenting with new materials, new concepts. So there as well, all the techniques that I talked about are very, very important. And then to conclude, we have some testimonials of existing customers using our SimCenter MICRET solutions. We have Huawei, who is using it, in this case, for improving their thermal simulation models. And they were very impressed with the accuracy that you can achieve by correlating the thermal testing with your simulation models and basically making your simulation models better based on the reality, the truth, which is your test. We have Denso, who showed us how they can highly reduce both the time and the cost to design their new ECUs. So in the design phase, they are using the SimCenter MICRET solutions. And then Nari, who claims that by using our solutions, they can greatly improve by 30% both the heat dissipation capacity and as a result also the lifetime increase of their, in their case, their IGBTs. So just some examples of customers' testimonials that use our solutions and what it really brings to them. And then to conclude, maybe as an ending slide, I would say here the overview of what we talked about. So SimCenter MICRET solutions, they're basically generating thermal metrics, doing a detailed model of the internal thermal structure of your electronic packages. It's an electrical method which is compliant to JEDEC standards, so it means it's a non-destructive, easy to use and quick method which uses the existing connections. So it's really easy to use, also very accurate because the measurements are happening very quickly and the transients, thermal transients, they go very quickly. So the accuracy of the measurement is crucial in having also a good, high accurate structure function. It's integrated with our thermal simulation solutions, as we saw, and especially it is ready for new designs, people working with new designs, new materials for the future. And basically what it does, it assesses, it characterizes in an experimental way the thermal properties like thermal metrics, but also helping you to improve the reliability and the quality of your electronic, being components, semiconductors, power electronics, or complete packages.